Hi. In this video, I'm going to explain Bode plots. So what is Bode plots? It's useful when we want to study the frequency response. And as we explained in previous lecture, the frequency response, it will be the voltage gain, for example, will be represented in y-axis, and x-axis will be the frequency. And we said that will be, in general, that's the frequency response. And the one in the middle, we call it the mid-band voltage gain. And we have the cut frequencies. We define it like two values: the low cutoff frequency, the high cutoff frequency. And at this cutoff frequency, the value will be equal 0.707 of the AV of the mid band. All right. The problem is, what is the range of this frequency that you are going to study? Maybe it runs from 10 hertz up to 100 kilohertz or 1000 kilohertz. So how can you divide x-axis to cover all this frequency? So it's hard if you are using linear scale. So the best solution to do this study, or to study the frequency response over a wide range of frequencies, is to use logarithmic scale. And using logarithmic scale, it will make it easy. So for example, if you have, I have here semi-log paper. What does it mean, semi-log paper? That's what we're going to use to do the Bode plot. As you see, the x-axis is divided into logarithmic scale. You see the distance here, the distance between the first unit and the second, and then start to get smaller and smaller, so because it's logarithmic scale. All right, it's different than the linear scale. Ordinary graph paper has a linear scale on both axes. A linear scale, the spaces between numbers are the same for all numbers. Like if you like this template I'm using, you can say, for example, the frequency is equal 10 hertz. So it depends the division, each one. Are you going to have 10 hertz, 100 hertz, whatever? If you have 10 hertz, you have 20 hertz, 30 hertz, 40 hertz. That's equal, you know. Equal division, equal scales. So in linear scale, the spaces between the numbers are the same for all numbers. But logarithmic scale is different. It's not like the linear. It's different. We have here the logarithmic scale on this axis, on x-axis, not everywhere. The x-axis, that's logarithmic scale. So, for example, if you choose this one, that's 1. You see 2, that's 2, 3, 4, 5. You see the distance between 1 and 2 is bigger than the distance between 2 and 3, and the distance between 2 and 3 is bigger than 4, and so on. So that's logarithmic scale, and that's why it's useful to represent like wide range of frequencies. For example, you might say, okay, if you are going to start from, let's 10 hertz, then you are going to multiply by 10 each I'm not talking about the small division. For every, that's the major division, and the little division inside, that's internal division. So that's 10 hertz. This one we multiply by 10, that would be 100 hertz. Multiply by 10, that will be 1000 hertz, mean 1 kilohertz. Multiply by 10, that's 10. Be like 10,000 kilohertz, and so on. So you can cover really wide range of frequency. All right. So this is the x-axis, will be like the representing the frequency in logarithmic scale. The other axis, the vertical axis here, it's normal. It's linear scale. You see the distance between each division the same. That's why we call this kind of sheet semi-log paper or semi-log paper. How you divide the vertical one? You divide the vertical one according to the range of your gain or voltage gain in decibel. So you might say, I'm going to represent each division, each vertical division into 20 decibel. So if this is the 0 decibel, for example, if we choose this is like 0 decibel, then that will be 20 decibel, 40 decibel, and then one below will be negative 20 decibel, negative 40 decibel, and so on, negative 6 decibel. So you choose where is your 0 decibel, and then each division can be represented by 20 decibel, 40 decibel. It depends on the range of the voltage gain in decibel that you calculate for any. So briefly, this axis logarithmic, and that represents the frequency, and the vertical one, this is the voltage gain in decibel, and the unit will be in decibel. Also in x-axis, the logarithmic scale, the distance between each or two frequencies, it's multiplied by 10, so we call it decade. So that's the unit. Remember the unit that being decade, and the other one will be decibel. So what's left now? How can we represent frequency response using this type of sheet, the semi-log there? All right, I'm going to have a general expression, and I will show you how you use Bode plot to represent the frequency response. Let's say that we have voltage gain given like that. AV, that's the voltage gain. Equal constant, which is the maximum, say, gain. It's a value like 400, 200, 300, and divided by 1 plus J or I, the imaginary number J, F frequency divided by FC, and FC should be given. Sometimes we call it corner frequency. And AM is like the maximum value. All right, it's a constant value, and maximum value, constant value, and also it's given. For example, just as an example, we can say that's equal 100 divided by 1 plus J F over 10 kilohertz. So FC, the corner frequency here, is equal 10 kilohertz, and F, we are going to change the F, the frequency, so you can find the voltage gain. Obviously, that's a complex number here that we have. So in complex number, always we are going to have magnitude and angle. Since we are going to have magnitude and angle, both plot will have two plots, one for the magnitude and one for the phase angle. Well, let's start step by step. How can we find the magnitude, or how can we plot the magnitude against frequency? All right, first you have to find the magnitude. We'll call it M, and then we are going to use this paper that it has a logarithmic and has decibel here. So obviously we have to express the voltage gain in decibel. So the magnitude will be equal to 20 log the magnitude of AV. Why I'm using magnitude? Because it's a complex number that we have in our hand here. And since we have a complex number, as we said, it will have a magnitude and it will have an angle. I'm not going through the all details because I know you did that in one course, but just I want to show you, if you have voltage gain given given in this expression, how can you do it? That's the definition for the magnitude. 20 log the magnitude of voltage gain. So we are going to use ideal Bode plot. It means we are going to divide it into two segments. One, when the frequency that you are going to choose here less than or equal to the corner frequency, in this case 10 kilohertz, or when the frequency is greater than the corner frequency. So if the frequency is less than the corner frequency, M in this case will be equal to 20 log the magnitude or the constant value 10. And this will be a constant value. So for simplicity, we can call this K, for example, after we find the value. In this example that we have AM is equal 100. So in this case, you can say it's equal to 20. If you just make 20 log 100, it's equal 20, and log 100 is equal 2. So it's equal 40 decibel. So in this case will be equal to 40 decibel. And the 40 decibel will be from in the range for frequency less than or equal the corner frequency. In our case, or in this example, the corner frequency is equal to 10 kilohertz. So I know already I have a corner frequency equal to 10. So just I'll go ahead to the Semilog paper here, and I will go and just divide the horizontal axis, and the 10 kilohertz. It's a good practice if you can find 0.1 of the F corner frequency and 10 times. So the corner frequency, just as I write this not just for myself, so I can choose the right scale. I say the corner frequency is given 10 kilohertz, so I need to know another two quantities, 0.1 FC, which will be 0.1 times 10 kilohertz, I get 1 kilohertz. And 10 times FC, it will be equal 10 times 10 is equal 100 kilohertz. So make sure the range of the frequencies will be between 1 kilohertz and 100 kilohertz, and the corner frequency is equal to 10 kilohertz, right? So it would be good if you have here 1 kilohertz. So you just shift it by one division, and you start with the minimum one, and this value is equal to 0.1 times FC, and FC is the corner frequency, as you said, it's given. You don't kilohertz. And then you multiply by 10. We agree that this is 1 decade, each one division 1 decade. So multiply this by 10. So if you multiply 1 kilohertz by 10, you get 10 kilohertz. And then you got 100 kilohertz, 1000 kilohertz, and so on. You can continue, all right? And it's good if you just put this is the corresponding to the corner frequency, and this corresponding to 10 times the corner frequency. So that's the first thing. We got from this graph that in the first region where the frequency less than 10 kilohertz, it will be equal 40 decibel. So, and by the way, you can have like the same range of frequency if you like to put it on the top here. In the case if that's 1 kilohertz, 10, 100, 1000, you know, everything kilohertz. And now in the range when, like again, when it's less than 10 kilohertz, it's equal to 40. So less than 10 kilohertz, so I will just mark it. That's 10 kilohertz. If you go down here, so anything below that 10 kilohertz, the value is equal to 40 decibel. See, that's what I'm trying to tell you, how you put the scales. So obviously I put 40 here just in the far top. So I will just rescale again the vertical axis. So I don't like to have 40 just in the edge, you know. So I'll just make it here. That's the 40 decibel. And then you have 20. You have 0, -20, -40. That's enough. It's just to know. So less than 10 kilohertz, the value is equal 40. So you go there, just make thick line here, so be obvious. Make it dark, and you make a straight line. What does it mean? This line, it means that the value is equal to 40 decibel, the voltage gain, for any frequency less than 10 kilohertz. That's easy. All right. So now let's look for the second one, which is really important. I want you to pay attention for it. For the frequency greater than 10 kilohertz or greater than the corner frequency, the equation in general will be equal to, we agree that 20 log AM, we call it K. So I'll just write here K minus 20 log F over FC. So that's the equation for any frequency greater than FC. So let me write it here. K is equal 40 decibel, the constant value, which is 20 log AM, minus 20 log F over FC, which is equal 10 kilohertz. I don't have to write kilohertz again because I know it's kilohertz. All right. How you sketch this straight line? This straight line, let me write it here. M, the equation M. I'm just writing this, the second equation. And by the way, it's M here, all right? This is M. It's M here. Let me write it here. It's M. So M is equal 40 minus 20 log F over 10. That's a straight line. This is the constant value, and this is the slope. So you can say that's like the equation will say y is equal mx plus c. You remember? This part is the y-intercept value, which is equal to 40. That's the constant value. And the slope here is negative 20. Let me write. The slope is equal to negative 20 decibel per decade. What does it mean? Slope equal negative 20 decibel per decade. I will go here to the sheet and I'm going to show you. You remember that what we said, that each division on the horizontal axis, we call it decade. And this is decibel. The difference is this 20, 20, 20. So first of all, the slope is negative. So I expect the straight line is going to be in this direction. This is the negative slope and this is the positive slope, right? So it should be like that. So you need 2 points. All right. So let me just go back here. So when you study, you can find the reference here. So if we agree about the straight line should be in this direction, and the slope is equal to negative 20 decibel per decade, it means this is 1 decade. It's very small. Let me make it bigger. We have space. That's the straight line. You can, of course, extend it. I'm just taking these 2 points. The vertical should be 20 decibel, and the horizontal should be 1 decade. So that will give negative 20 decibel per decade. So these 2 points, when you choose, it choose in a way, if you move 1 decade in this direction, all right, then you can go up 20. All right. Or you can say if you know this point first, let's say that you know this point first. So say you go down 20 decibel. And then you go horizontally 1 decade. If you do that, so these 2 points, if you connect straight line, it will be negative 20 decibel per decade. That's what I'm going to do. So that's start from 10 kilohertz. Okay, we'll stop here at 10 kilohertz. Remember, this is the 10 kilohertz. So this is the point. So let's just make it dark. So this is the point where we start. What you're going to go, you are going to go down 20 decibel. 40 decibel, you have 40 decibel here, you have 20 decibel here. So I'm going down 20. So I get down 20, and then I go 1 decade. So I move horizontally to the right, just 1 decade. This is 1 decade, right? So I got the second point here. So I have now the 2 points. If you connect them, you will have a straight line of slope equal to negative 20 decibel per decade. So I will go ahead and I will connect. Great. You can extend it. So this line equal negative 20 decibel per decade. You are done with the first part of Bode plot. That's how you do it. And we have one corner frequency, which is equal to 10 kilohertz. Before the corner frequency, it's constant and equal 40 decibel, and that's 40 decibel. Remember, that was equal to 20 log the constant value, which is usually will be the mid band voltage gain. And then going from the corner frequency with a straight line has a slope negative 20 decibel per decade. All right. Before I leave that, I will just tell you about a point. Maybe it's not mentioned in the textbook, but it will help you to find the slope of any straight line, sketch or plot it on this semi-log paper. If you have any straight line, any straight line in logarithmic paper, and let's say you have point here, not 1 decade, just you have odd points, because maybe somebody asks, what about if I don't have 1 decade? How I do that? Well, this point, let's say that the frequency, of course, you have 2 axes. You have the frequency. This is the axis of the frequency, and this is the axis of the decibel, right? And remember, this is divided to decade and logarithmic. This is logarithmic, right? So every point has value of the frequency. Let's call this point A. So the frequency is equal FA, and the value is equal A decibel. And this one point, call it point B. So the frequency is equal FB, and the decibel is equal B decibel. So what does it mean? It means that if you have the logarithmic scale, I will just show you now. If you go there, that's the frequency. If you go down here, that's FA. You go down there, that's FB. And the vertical axis, the decibel. That's the decibel. So if you want to know the value, so just to go ahead and write it. So you have the frequency here is FA on logarithmic, and this is logarithmic. Remember, logarithmic scale. And this one decibel scale, that you have A decibel, and this one B decibel. All right, and this is FB. How to find the slope of this straight line on the Bode plot? Slope will equal which point you're going to take, B minus A or A minus B. Both are right. I would say B minus A. I would take this first point and then subtract from this point. All right, but you can choose. Once you choose, I'll say B minus A. So the vertical value of point B is equal B decibel. So we have B, and its frequency FB. Remember FB. All right, that would be log. Why I'm writing log FB? Because it's logarithmic scale. Minus A point. The A, this is the point A. It has equal value to A decibel, and I subtract also its corresponding frequency FA will be log FA. So it will be B minus A divided by log. You can write it FB over FA, because when you subtract the logarithmic and make division. So that's a nice formula I used when I was a student to find the slope of any straight line plotted in semi-log paper. That's easy. Now say somebody say, okay, can we apply this formula to the straight line? You got to know that if you did it right, or yes, you can check your rules. You have 2 points here. That's point B and that's point A. Point A, what is the frequency here? Okay, the frequency here is 100 kilohertz, right? So let me write on the side here. So you have FB is equal to 100 kilohertz. And what's the corresponding value of B of the decibel? Well, I will just follow decibel here. That's equal to 20. So NB is equal to, oh, this is A or B? No, I think this is A. We said A and this B. It doesn't matter, by the way, name, but just I want to follow the same thing. I think we call it A, this point A. So that's if A is equal 100 and A is equal 20 decibel. What about the second point, if B? That's point B, that's 10 kilohertz. So if B is equal 10 kilohertz, and the value of B, let's just go here, that's equal to 40. So it's equal 40 decibel. All right. So let's just take this one and go to our equation that we did. Copy and see if it's right or wrong. That's the equation we did. So let's do the example that we have. All right. That's the data we got. So the slope will be equal to, the value of B is equal 40 minus the value of A is equal 20. I subtract this value from this value, and then I'll subtract FB minus VA, but by using log. Write it nicely. Log FB, which is equal to 10 over FB over 100. So 40 minus 20 is equal 20, and 10 over 100 will be 1 over 10. So log 1 over 10 will be equal minus 1. So the slope is equal negative 20 decibel per decade. We got the same answer. So that was like a helpful formula if you have any 2 points to find the slope on this. Okay, so we learn how to sketch the magnitude on Bode plot. How can we sketch the angle? All right. By the way, this is not the exact Bode plot. It's ideal Bode plot, which is acceptable. The phase. All right. This is the equation. So let me take a copy of this equation, and we explain how can we do the phase with the frequency. All right. In this equation, all right. Of course, when you want to find the angle of the top is equal 0. So you say the angle of the voltage magnitude, let me call it phi. The angle of the voltage gain AV will be equal the angle of the top over the angle of the bottom. All right, the angle of the top, it's a constant, so the angle will be equal 0. So it's 0. The angle is equal 0. Right, it's constant. When you say 5, 6, 7, it's 0. The angle on the bottom, you get it by the tan. So in the bottom will be tan minus 1, the imaginary over the real. So if you do a triangle like that, that's not a nice triangle. This triangle, the imaginary part equal F over FC, and the real part is 1, and this is the angle phi, whatever. So tan minus 1, the imaginary, was F over FC over 1. That's the angle we get. So to get it in the top, if you move tan minus 1, F over C in the top, you'll be minus. So phi will be equal to minus 10 minus 1 arctan of F over FC. So that's the formula for the angle. You can use it to calculate any angle. In our case, if C is equal to, I believe, 10 kilohertz, so in our example, phi will be equal to negative 10 minus 1 f over 10 kilohertz numerically. So it's easy. You just can plug the values for f starting from 1 hertz up to 1000 kilohertz, and you get them. But again, I'm going to use ideal plots for the phase. And to do that, we are going to do the following. We are going to divide the axis of the frequency. As we said, we have three important values. There is one at FC, which is equal 10 kilohertz. That's the value for the F. And before we divide by 10, before it will be 1 kilohertz. And they multiply by 10, this one will be 100 kilohertz. That's important, right? Then what? Then you will do the following. I don't need that one. No? You do the following. You will make a table, and you'll say that's the frequency. You can start by 0. Of course, you can represent 0, but just to get an idea. And then you put this angle, the first one you face, which is 1 kilohertz. And then you have 10 kilohertz. Then you have 100 kilohertz. And you say, okay, we can get like a huge value. All right. That's the phase. Remember, that's the formula of the phase angle. Phi is equal negative 10 minus 1 f over 10. First of all, if f is equal 0, so what is the value for f over 10 or f over fc? Will be 0. What is phi? Phi is equal 10 minus 1, 0. That will be equal to 0 degree. So that's the one. If you go for infinity, what is the infinity over fc? Will be infinity. If you divide infinity by 10, is equal to infinity. What the angle that its tangent equal to infinity? That's 90. So you add the negative sign, you have negative 90. So you already know the range of the angles is between 0 and negative 90. It looks like so decreasing. Now you look for the one at the corner frequency, which is 10 kilohertz. What happened when it's equal 10? So you divide 10 by 10, or divide f by fc. In this case, will be equal 1. What is the angle that its tangent is equal to 1? That's 45 degrees. So it's negative 45 degrees. So you know it's from 0 to negative 90, and at fc, at the corner frequency, negative 45. Remember, this is equal to 0.1 fc, and that's 10 fc. So this 10 fc, that when it starts to get the value that you calculate at 0, which is 0. And then when you multiply the corner frequency by 10, it will take the value, take the value of the one when you calculate at infinity, that will be negative 90. So at fc, it's negative 45. At 0.1 fc, it's equal 0. At 10 fc is equal negative 90. So you will go to the semi-log paper here. And let's say that the top part, I'm going to use it for the magnitude, and the bottom part, I'm not going to make it decibel. I'm just going to do the phase. And I already know it's... it will maybe I will do the phase angle in this direction. So let me just put the scale here. I know from 0 to negative, so I have negative 90 here. Let me just clear this one. So change the color. So that's negative 90, and then you got negative 45. So I'll make it like every division here 45, and that will be 0. So the space between each two division, vertically it's 45 degree, and I know it runs from 0 to negative 90. That's FC. At FC, we found it's equal negative 45. You put a straight line here. At 10 FC, it's equal to negative 90, and at 0.1 FC will be equal to 0. So what you will do, you will find a straight line. And then when the frequency is increasing up to infinity is going towards -9. So you make a straight line, it's already fixed. And when it go below 1 kilohertz, below 0.1 FC, it will be at the same value of 0. This is 0 degree, you see? So that will be the phase diagram. So it depends on 3 points. That's the ideal Bode plot for the phase angle. It depends on 3 points. FC, 0.1 FC, 10 times FC. That's the way that you can do that. Excellent. So I think it's an easy way to plot the Bode plot using ideal plotting for the frequency response. This example, it's a numerical example, but maybe somebody wonder how can you apply this in electronics. Okay, let me first apply in a circuit, because what's happening here, we said that when you have transistor, you have capacitor connected to resistor. So I will just focus on a circuit, simple circuit first, and this circuit, a lag circuit, consists of resistor and capacitor, and this is the source. This is the source of the signal, and that's the resistor, and that's the capacitor. So what's happening here in this circuit, I want to find the corner frequency and the constant magnitude. So that's my job, how to find the value for it. Well, you can start using the circuit to write the equation down as you learn in circuit 2, all right? And then after that you apply whatever you're going to apply in magnitude or phase. I will show you how to write the equation of this circuit, and then I will extract the information that we need, but we have to give the value for the resistance and the capacitor. So let's assume that the resistance is equal to 5 kilo ohm and the capacitance is equal to 100 picofarad. 100 picofarad means 100 times 10 to the power of -12 farad. So we want to do the Bode plot for this one. All right. Of course, it doesn't matter. I give you the magnitude for Vs, because in the end, when you do the voltage gain, you will say the output voltage, which is across the capacitor, divided by S. So just I want the result. So let's write the question. Go ahead and just tackle the problem here. How you find the output voltage across the capacitor using circuit analysis? It's a voltage divider. But first you have to find the impedance of the capacitor. What is the impedance of the capacitor? Well, the impedance of the capacitor is equal to minus JXC. So the impedance of the capacitor is equal minus JXC minus J, and you know XC, the reactance, the capacitor reactance is equal 1 over omega C. So if you do it in frequency, it would be minus J 1 over 2 pi FC. That's the impedance of the capacitor. Voltage divider rule to find the output voltage, you will say that the output voltage V output is equal to the input voltage of the source times the impedance of the capacitor ZC divided by the impedance of the capacitor plus the resistor. Okay, so what you will do now, you want to find the output voltage over the input voltage will be equal ZC over ZC plus R. I will divide the top and the bottom by ZC. So ZC, let me make it in steps so you'll understand. So the voltage gain now in V, which is equal the output voltage over the input voltage, will be equal ZC over ZC plus R. I'm going to divide both by ZC. So I divide this by ZC. divide this by dc to make sure I didn't change anything in the equation. So the result, dc by dc is equal 1, dc by dc equal 1, r over dc. I got this nice equation, but I want now to know what is r over dc. dc, we know that dc, I just wrote here, is equal minus j over omega c. So minus j over omega c, or 2 by fc. And we know that 1 plus 2 by fc, it will go on the top, 2 pi fcr rcf, and minus j when go on the top becomes like j. So I wish if I can write this 1 plus j f over fc, because this is what just I explained. I explained to you how can you do the Bode plot for this given in this form. That's what we just explained, right? 1 plus j f over fc and am on the top. So I want to do that. So I wanted this equation, I have 1 over 1 plus j, whatever, is I want to make f over c. So just you look for these two terms and equate them, compare them. That's both are j, f over fc, and this is, that should be equal f over fc, right? So I will just equate them to know what's my fc. 2 pi r c f equal to f over fc, I'm sorry, f over fc. So f cancel f. So 1 over fc equal this. So I get fc is equal 1 over 2 pi rc. So that's the corner frequency. That's all what you need. How to find the value of it? It's already given. So I'll say fc is equal to 1 over 2 pi r. R is equal 5 kilo ohm. 5 times 10 power 3. And C is equal, I believe it's equal to 100 picofarad. 100 times 10 to the power of negative 12 farad. That will give the frequency. Doing this, I did that in the calculator right now. It's equal 3.183 times 10 hertz, because I got everything in the unit. And I want to make it kilohertz, so I divided by 1,000. So I get 318.3 kilohertz. So the corner frequency is equal to 318.3 kilohertz. That's the corner frequency. What about AM? AM, obviously, it should be here AM. So AM is equal 1. You compare, so AM is equal 1. So what do you expect the Bode plot? I expect the following if I get the same. I think I have one here. Let me just sketch for you here quickly. So if you have, this is the frequency. As we said, you have the FC here, which is equal to 118 kilohertz, the frequency in kilohertz. And you get divided by 10, 31.8, you multiply it by 10, you get 3180. Now, AM is equal 1, so what's your K? Your K is equal 20 times log AM. 20 log 1. Log 1 is equal 0, so your K is equal 0. So if you say that this is your 0 decibel, this line, this make red line here, that's represent the 0 decibel, it will be running 0 up to the corner frequency. This is your FC. So it will be constant. Let's just make it thick line here, going from lower frequency up only to this point. And after that, I expect it's going to be like slope negative 20. You know how to do the slope equal negative 20. We'll go down by 20. So I'll make this negative 20 decibel. and the top positive 20, negative 14. So I make the distance here is 20. So I go down 20 and then I go 10. That's why I'm dividing everything to 10. Then these are the 2 points. When I connect them, I get the straight line of slope equal to 20. You can extend it, of course, all right? Can make area. So this is slope equal to negative 20 decibel per decade, all right? Good. So we did the magnitude. What about the phase? We need the three frequencies we have here. FC 0.1 and we know it runs from 0 to negative 90. So just I will make the axis here 0 degree. That's 0 degree. 45. Negative 45, I'm sorry. And negative 90. And that's 0.1 FC, and that's FC, and that's 10 FC. Up to 0.1 FC, anything before will be 0. So it will be going in this direction along 0. At FC, I'm sorry, is equal negative 45. At 10 FC will be equal to negative 90. So you have a straight line like that. And then will be negative 90 beyond the 10 FC. And that will be the phase against the frequency F. And we are done with the frequency response. And this circuit, it's called like lag circuit. It's important with the amplifier because always you will find capacitor connected to the output or the input. So that's enough, that's it. And I hope that you got it. And then I will give you some exercise to work on. Okay, thank you.